Hello calculus students. Today we're going to introduce a new unit, and it's probably the last one or the second to last one you're doing this year in Calculus 1. So we're going to introduce the unit on differential equations. So differential equations are a really big topic in college. Engineers take several courses in differential equations usually because differential equations describe how things change. So if you're watching this video, it'd be beneficial if you could have this handout in front of you. That's definitely the way that we're supposed to do this. This handout was made by Larry Peterson in his workshop I attended, and I'm pretty much going to use it to introduce differential equations the way he does via slope fields, because slope fields are part of the AP curriculum, but also because I think it's a really good way to visualize the change and flow that are a big part of differential equations. So I just really want to write that at the top. Is that differential equations, so that's often abbreviated as DEs. Sometimes there's an O added here, sometimes there's a P added here. That's for ordinary differential equations or partial differential equations. We're just going to be working with one variable, ordinary differential equations this year. So differential equations are related to how quantities change, to changing relationships. I think that should make sense to you, because remember, when we do derivatives like dy dx, that is specifically the change in y over the change in x. You can use the Greek delta if you want and think change in y over change in x. But differential equations in general just describe how things change. So you might have a really simple differential equation like this one. You can see this one right here in Mr. Peterson's handout. This differential equation is dependent on y and the natural log of x. That's how you describe the change in y with respect to x. Other differential equations can be, of course, much more complex than that one. You can have differential equations, for instance, that are like, y triple prime. You might have 2 times y triple prime minus 4 y double prime cosine of x plus 7 over x equals 8. And that's a third order differential equation, ordinary differential equation, because it's got a third derivative in it. And it would be pretty complex to solve. So solving differential equations is something we're going to build up to a little bit, but not really the focus of today's lesson. I think we'll start solving them very simply today. And the idea of solving a differential equation, so I'm going to write that down too. To solve a differential equation, or an equation, in other words, with derivatives in it, you are looking for y, or the function that satisfies the equation that has a third derivative times 2 minus a second derivative times 4 times cosine of x plus 7 over x, and gives you 8. So you're solving for y when you're solving a differential equation. And like I said, that's not going to be the focus of this first lesson. We're going to be more picturing differential equations and thinking about this up here, thinking about change, and working with the terminology as well. There's a lot of vocabulary here, and I think the vocabulary should go well and tailor itself well to other derivative type of situations that we've been studying this year. Okay. So you can read his handout here. It talks about how an initial value problem relates to a differential equation, and that's how we're going to kind of bring in the concept of a slope field. So let's say we have a really simple function here. So this is kind of the solution. It's like they gave us the solution to the differential equation to begin with. So they say write the derivative from that. So my class a second ago pretty much picked up quickly that the derivative from that, y prime, or I'm going to like to use Leibniz notation here, dy dx is equal to just x for this differential equation. So there's the differential equation. There's the solution to the differential equation. What I want us to do is think about how a slope field plays into this. So the slope field is a way to construct the solution or family of solutions to a differential equation by looking at the slope one point at a time. So if we think about the origin here, the point at the origin is 0, 0, so dy dx would be 0, so we'd have 0 slope right there. If we think about here, the x value is still 0, and see how this differential equation just depends on x. So any x is going to have, if it's x equals 0, a 0 slope. So we're going to have a little piece of slope that's 0 for those and for these. If this is 1 right here, then dy dx would be equal to 1 for all these points. So we'd have a slope of 45 degrees. Slope of 1 for all these different points. Now that's just because this differential equation is only dependent on x, so I can make this shortcut. You want to look for patterns when you're doing slope fields. So if I put like this point in, looks like that point is 2, 1, then the dy dx is 2, so it's going to be steeper. So I'm going to try to draw a little bit steeper, and that's going to be true for all these x of 2 grid points. Over here the slope is going to be steeper at x equals 3, and so forth. Over on this side the slope is going to be 45 degrees at -1, so that's supposed to be 45 degrees. I'll try to make it nice 45 degrees. And then it's going to be -2, so that's a little bit steeper over here. And -3, a little bit steeper over here. So you can see I'm not being super careful with this. I'm just trying to picture the pattern of the entire field. So how an initial condition relates to this is if I say the initial condition is like 0, 0 at the origin, think about kind of dropping a leaf. So you're kind of up above this point, hovering above, and you drop a leaf and it hits into the field. And you're not supposed to play dot to dot here. You want to picture what happens to that leaf over time. Where does it flow to? So don't play dot to dot, and you can see that the black line here is kind of already picturing where the leaf flows here. The leaf would flow that way if it were to go that way, and if it were to go this way, the leaf would flow this way in the current of the slope field. So that's the particular solution. That guy right there is the particular solution to this differential equation, which they're arguing is 1/2 x squared. It looks like a parabola, doesn't it? Maybe a little bit flatter. If I were to give you a different initial condition, let me do, I've already got red going, let's go blue. If I were to give you a different initial condition, for instance, let's say -3, 0. At -3, 0, -1, 2, 3, you drop a leaf here. Where does that flow to in the field? It must flow something like this, and then something like this, right? So that would flow to create a completely different member of the family of solutions. It's just a different particular solution. So a slope field in general shows the general solution. Let me write that down. A slope field helps you picture the family or general solution to a differential equation. All right? So let's move on and look at another one. So this one, it'd be good if you pause the video right now and try it on your own. So it says sketch a function that matches the slope field. Let me give you a couple particular solutions to sketch. So let's do two different ones. Let's do one with an initial condition at, let's say 0, 2. And then let's do a totally different particular solution. We'll see where it flows if we pick an additional condition of, let's say, how about -2, 0. So pause the video right now and try to trace those out. See where your leaf flows when you drop it. Alright, so for me, 0, 2, I think these are scaled. It's a little hard to see, but this is supposed to be where that falls. So if I have that one, then it looks like it's going to be something like this, right? If I drop it at -2, 0, that's over here. That looks like it's going to flow down this way a little bit more. Maybe something like that, if you get my idea. So now that's a pretty rough sketch, but that's what we were supposed to do. So think about what family of solutions appears to match this slope field, like Mr. Peterson's question right here. So you might not be sure exactly, but I think that this is supposed to be parabolas. We've got an x squared. I think this is actually parabolas with slope of 1, so I think I should have made this dip down a little bit lower, but you get the idea. The other key ingredient is if it's the family of functions, if it's not just one of these in particular, like the red or the green one, then it's x squared plus what? I think we've used this kind of idea before recently. I think it's x squared plus c for the family of solutions. And if you want to find a particular solution like that green one, you can just plug in. So remember, we're seeing the solution, or y, and that's the whole family. If I plug this in, I can get the particular one. Let's plug it in and see if it makes sense here. So I plug in 0 for y, I get 0. If I plug in -2 for x, I get -2 squared plus c. So that's 0 equals 4 plus c. So that says c equals -4. So that says my solution, particularly, is y equals x squared minus 4. So look at my green curve there, and I didn't do a very great drawing. Let's try to do it a little bit better. If I try to draw it a little bit better and see where this flows, I think I was supposed to go down a little bit more. And does that look like the parabola x squared shifted down 4? It looks like more like kind of 3 for me. But I think that's just because of my failure to follow the flow of the field more accurately. I think I should have been a little bit more vertical here if you look at this particular slope lines. And that's a tough call, but remember the whole point here is to picture the solution. Alright, so now another thing that'd be good for you to do right now is try this one. Let's skip number 3 and let's go straight to number 4. And try number 4 out and sketch all the little pieces of slope for this differential equation over here. So pause the video, see what you get. Alright, so I'm going to start. This one looks like it's only dependent on x again. This guy is just dependent on x. So I think it's going to have a vertical orientation. And that is terrible handwriting. Sorry about that. Alright, so if I plug 0 in, I get 1/3, right? So 1/3 is pretty flat, so I'll go like that. So this still has an x of 0, so that's going to be the same slope right there. If I plug in something like, I'll just do it over here, x equals 1, then the slope is going to be 1/4. That's even shallower. So I'll try to make my slope lines even shallower. So the last one, if I plug in x equals 2, it's going to be 1/5, and you can kind of start to see the pattern developing here. So I think that's even going to be shallower than the previous one. So it's tending, as we approach infinity on the entire family of solutions, it's tending to look flatter and flatter and flatter. By the time we get out here, it's going to look almost flat, even though it's not totally flat. That's the idea. So what about if I plug in -1? If I plug in -1, I get 1/2. That's a little bit steeper. If I plug in -2, I get 1/1, which is even steeper. And if I plug in -3, I get 1/0. That is undefined. So that's going to be vertical. So over here I have a vertical slope at -3. Then it's 1. So nice 45 degrees there. And you can kind of see this pattern developing, right? If you plug in -4 and finish this field, hopefully you did, you're going to get -1 for the slope. So over here it looks like this. Okay, so now we can think about different initial conditions here, but I think the main point is that if you drop something like right here, let's say our initial condition was right there, then it's going to flow down like this. What kind of shape is this? I think you should be able to guess that the kind of shape this is a logarithm shape. Where does that come from? Let's practice actually solving this equation for the very first time. So I'm going to go down and do what's called separate variables here. So I'm going to separate my y's on one side, and my x's are mostly over here. I just need to multiply the dx up to that side. So I've got this dx. This is what we like to do for the AP exam. It's the technique called separating your variables. Once they're separated, you can just integrate both sides of the equation to solve. The integral of dy is, of course, y plus a constant. The integral of this guy we've been practicing lots lately is the natural log, and technically there's an absolute value on that natural log, right? Plus a constant. Now those constants are both just arbitrary, so I can really subtract this one this way and absorb them together in one grand constant. So I'll just call that one C. What you call it really doesn't matter. Okay, now why does the absolute value really matter here? I think we've talked about that kind of as a technical rule so far. Why does that actually matter here? Well, I think it matters because the natural log just looks like this, right? The natural log usually just looks like this, and it has an asymptote that's shifted left by 3. Can you see how this is shifted left by 3? So I think that totally matches our slope field, but our slope field also had some values over here, right? And that's because this natural log absolute valued really lets you produce the natural log on this side as well. So it gives you some symmetry. That's what the absolute value of x does, is it's a kind of like a y-axis reflection. Okay, so nice little technical follow-up there. Let's do one more problem before we quit this video. It's kind of like an AP problem, pretty easy one. Bring together everything we did. So if you're watching the video, I would pause it now and try to just do this totally by yourself. I'm going to go a little bit quickly. Alright, so we want to sketch a particular solution through 0, 1. That's right here. Looks like that goes down like this. Looks like there's an asymptote down there. That was pretty ugly. Let me try it again. Maybe like this. There's a little better. Okay, and then they want a different particular solution for B through 0, negative 1. Okay, over here, slope field looks like it's going this way. And it looks like it's going back toward that same asymptote. Okay, part C, what familiar family of functions do these two solutions resemble? Well, I think these are exponential, aren't they? Okay, and finally, verify your guess. I think we're going to solve by separating variables like we just did. Now this one is y-dependent, so if you look at the slope field here, you'll see that it's not the same on any vertical line, x. The slopes are totally different, right, going down. But if you go across y, the slopes are the same. That's because this is a y-dependent slope field. Some slope fields depend on y alone, some depend on x. More often than not, they depend on both, and those are little ones we're going to build up to. Okay? Alright, so let's solve this guy. Separating variables. dy, let's divide the y to the other side, multiply the dx up the other side, and integrate. Integrating, there we go. So I get the natural log of the absolute value of y equals x plus my grand constant for both sides. Okay, now I need to solve for y, so get rid of logarithm, u exponential. I've done that, so I have y equals e to the x plus c. And now for a subtle step of algebra, I think you can write that like this. This is a really important algebraic step. Don't underestimate it, please. So that says that, remember, that's just that rule of algebra that says if you have this, you could add the exponents. I'm kind of using that rule backwards. Man, what an important algebraic step. Anyway, this part that I've circled is really just another constant. So let's give it a new name like k. So that's k e to the x. This little problem is classic. What we got from here and how we got the answer, I would really just memorize that if you have a differential equation dependent on its y variable, you're going to get an e to the x answer. And for us, that makes sense because I see e to the x is up here. If we plug in, let's just do this one for instance. If we plug in 0, negative 1, we're going to get y equals k e to the 0. Oh, I shouldn't have y there, right? I should have negative 1. So that says anything to 0 is 1, so that's this. So that says k is negative 1. So that says our solution, our particular solution, this is the family of solutions. Get cleaner here with my writing. Our particular solution, though, for this particular curve up here is going to be negative 1 e to the x, or just negative e to the x, which makes sense because it's e to the x, which is this one, flipped over. Okay. You know, I think I'm going to do one more example. So for my class, I gave them this one for part of their first homework assignment, along with the matching worksheet that's attached to your handout. I think you should do this one yourself and then check your answer. Okay, so the same process. We've got a slope at a point, so I'm not even going to talk here. I'm just going to do the problem, and you guys can watch and check your work when you're done with your own. Alright, so calculate the slope at that point. Alright, let's do it. let's go and look at 2, -1. Does it look like its slope is about 1? Yes, it does. Okay, check. Starting at 0, 2. Okay, I'm going to erase that part down there. 0, 2 up here. Okay. Draw the particular solution, and what shape is it? Let's see. So I think it looks like it's going about like over here, and then flowing like this way. Mine looks like a football. Something like that is the shape. So I think this looks like an ellipse. Maybe a horizontal ellipse. Alright, then it says to solve. Find the unique solution and see if it makes sense. So I'm going to go back to the equation and separate my variables. I think I'll go multiply that by this. Hold on one sec. Let's go 9y dy equals -4x dx. Cross-multiplying action. Alright, integrating action. So there we go. Alright, I'm going to plug in my initial condition, which is this, right? So let's see what we get. That's 9 times 4. Oh, did I make a mistake? I think I did. I don't think I integrated correctly. What's the integral of y? It's not just y squared. It's y squared over 2, right? X squared over 2. So this is also supposed to be over 2. Alright. This is -4. If I'm plugging in 0. So that's 0. This is 36 over 2. That's 18. Okay, so let's see if this makes sense. Does that look like an ellipse to us? So that means we have our solution is 9y squared over 2 equals, that just reduces to -2x squared plus 18. Well, this doesn't look like an ellipse to me. What the heck? Well, maybe we should try to simplify it and make it look like an ellipse. Don't we want to usually add it and make it look like this? And if it's an ellipse, truly, then shouldn't we be able to get a 1 over here if we divide? Let's try that. So that would be x squared over 9, right? Plus, let's see, that'd be 9 halves. That'd be like y squared over what? Maybe we should do a little fraction scratch work over here. So this is like 9 halves times, you can think about flipping that fraction like that, right? Like this. So that would be like reduce, and that'd be 1/2, and 9/18 is 2, so that's 4 that's underneath there really equals 1. Oh, there's a nice ellipse right there. It's going out 3 in the x direction and 2 in the y direction. Look at that. 3 in the x direction, 2 in the y direction. There's B, the semi-major axis. There's A, the semi-minor and semi-major axis. Totally, it looks exactly right. So everything fits together. So I hope you found this to be a useful introduction to slope fields and differential equations. I'll see you next time.